The formation of imines and enamines. In this lesson, we're dealing with the nucleophilic addition of amines to ketones and aldehydes. And it turns out when you add a primary amine, you get an imine as the result. And when you add a secondary amine, you get the enamine as a result. Now we'll take a detailed look at the mechanisms for both these. It's a little bit of a pain in the butt for some of these acid catalyzed mechanisms. We'll also look at the reverse reactions, the hydrolysis of imines and enamines, and how to predict the products for those. And then we'll quickly revisit the mechanism for the Wolff-Kishner reduction. So it turns out we need to learn about imine formation, or at least an imine derivative, before we could go back and revisit that mechanism. Now, this lesson is part of my organic chemistry playlist. I'm releasing these lessons weekly throughout the school year, so if you want to be notified every time I post a new lesson, subscribe to the channel and click the bell notification. Okay, so we're going to start with imine formation, and as we said at the beginning here, when you take a ketone or aldehyde and add a primary amine, you'll form an imine. Now, I say primary amine, it technically could also be ammonia. This could just be NH3 with an acid catalyst as well. So, but I'll start with a primary amine, and I first just want to take a look at predicting the product here. So, turns out net result when you add that primary amine is that your carbon-oxygen double bond becomes a carbon-nitrogen double bond, and the nitrogen is going to retain its bond to either one hydrogen, if it's ammonia, or at least just the carbon chain in this case instead. And then these two H's and that O are going to be water given off in the process, so your byproduct. And it turns out this is totally a reversible process, so you can totally go backwards with this. Shift the equilibrium back towards the reactants. So it turns out acid catalyzed in both directions, and so you need to add water with acid to shift the equilibrium back according to Le Chatelier's principle. And water with acid is H3O+. And when you're doing the reverse reaction, we refer to this as the hydrolysis of our product here, which is an imine. So a couple things. An imine is also called a Schiff base, and I spell that out and say it very carefully, because if you just say Schiff base really fast, it sounds almost like something else, so be careful. So, but you're more commonly going to see it called an imine. And it turns out we've got a couple of imine-like derivatives that you should be familiar with as well. So it turns out if instead, let's say we had used this right here, instead of a primary amine, we're using what's called hydrazine. And once again, we're going to end up with a carbon-nitrogen double bond. And then your nitrogen's still going to have bonds to, it's going to lose two hydrogens, but still have a bond to another NH2. And this right here is not called an imine, but is called a hydrazone. So it turns out this reagent right here is hydrazine, and the product it results in is a hydrazone. And similarly, if instead of a carbon chain or a hydrogen, that other R group is actually a hydroxyl group, so now you're still going to end up with a double bond of nitrogen, but now it's going to be bonded to an OH here. And in this case, we don't call this an imine, we call this an oxime. So the reagent here is called hydroxylamine, and the result here we call an oxime. Mechanistically, it all occurs the same way, and these are all analogous, but they do have distinct names. So again, if your R group here is going to be a carbon chain or a hydrogen, we call this an imine. So if it's another amine group, we call this a hydrazone, and if it's a hydroxyl group, we call this an oxime. Cool. So now let's dive into the mechanism here, and we're going to need a little bit of room for that. So when I'm predicting products, I like to show some specific examples, but I want to do this very generically for the mechanism. So a couple things to note. So we've got an amine in acid. Well, amines are bases, and so it turns out along the way here, we're going to form some of that in our solution. In fact, there will be an equilibrium between the base form and the conjugate acid form in that solution. And depending on the pH, the lower you make the pH, the more of the acid form you'll have and the less of the base form. Well, the base form is our nucleophile, and we need it to act as a nucleophile in this reaction. It'll also be what acts as a base in the reaction. The conjugate acid form, every time we need an acid, it's what's going to be actually acting as the acid form. And again, if you make the pH too low, well, then you end up lots of this and hardly any of this. And if you don't have hardly any of this, you don't have any to act as the nucleophile or a base for the mechanism. So it turns out there's an optimal pH for this, and I think it's somewhere around pH 4 to 5 where you do this reaction. If your pH is too much lower than that, well, then you have too much acid, not enough conjugate base formed for the amine. And if it's too much higher, well, then you have a lot of the conjugate base and not so much of the conjugate acid, and it's not, going to be acid catalyzed all that well. So keep that in mind. And we're going to see the mechanism here is going to be 6 steps long. It's a pain in the butt. Acid catalyzed mechanisms you're going to learn are the bane of your existence. If you didn't realize that with acetal formation, we'll reinforce it right here. But little difference at the beginning here. So it turns out that amines are better nucleophiles than alcohols. And so like with the acetal formation, we had to protonate our ketone or aldehyde first before the weak nucleophile alcohol could attack. But amines are better nucleophiles, and they actually attack first in this case. And so we're going to do nucleophilic attack to start off instead. So big key difference here. So leading us to this lovely intermediate right here. You'll also notice that all the steps are reversible when we deal with the mechanism. Just like we said, it can be reversed with H3O+. So we'll draw these all as reversible. We form an alkoxide, which is a strong base. We also have a quaternary amine, which is a weak acid. And so both are charged, which leads to, some reactivity, some lower stability. But the strong base is more reactive than the weak acid, so we'll end up having the strong base react first here. So next thing we'll do is just simply protonate that oxygen. And again, anytime we need to protonate something, this is the species we will use, a protonated amine. All right, so we've got this lovely intermediate, and hydroxyl group now is neutral, but we still got a positive formal charge over here, and he's a weak acid, and so what we're going to do is deprotonate. And you're going to have a lot of acid-base reactions going on here. So when we need to deprotonate, we just draw another equivalent of the conjugate base. In fact, actually, we don't even need to draw another one in because I forgot to draw one right here. When this guy got deprotonated, he formed the conjugate base, and we'll use him as our base. Come and pull off one of those H's, deprotonate. And when we deprotonate, he turns into his conjugate acid as well. And now we've got a neutral species, so there's nothing particularly reactive. So when you're trying to predict what's going to happen here and stuff like this, part of it is memorization, and part of it is making sense of the reaction. And so, getting this far, where we dealt with the things that were charged one at a time, the more reactive before the less reactive. But here we've got nothing charged. You want to keep in mind where we're headed. We want to end up with a carbon-nitrogen double bond, and that OH should not be there. Well, is OH a good leaving group? No. And so just like we saw with acetal formation, if you have something that's not a good leaving group and you want to make it a good leaving group, protonate it. And so it turns out you'll see a general pattern for some of these acid catalyzed mechanisms. When you want something to leave, protonate it. When you want something to stay, deprotonate it. Well, I definitely want him to leave, and so we're definitely going to protonate him. And again, we're always going to use the protonated amine in this reaction for the acid when we need one. Cool. And another thing you'll notice about the mechanisms here is that every time you protonate something to make it a good leaving group, it's going to leave in the very next step. So that's what we're going to want to do here. Water is a good leaving group, and we're going to have it leave. Now, in this case, it looks like we're about to form a carbocation right on this carbon after water leaves. And just like with acetal formation, though, it's going to be resonance stabilized because right next door is an atom with a lone pair of electrons. And often, again, just like with acetal formation, rather than showing both resonance structures, we often just show one. Now, if you show both, you're technically more correct. But like I said, most of the time, you're probably going to see this mechanism with only one of them drawn, where we use the lone pair to form a pi bond there. And so in the next step here, we're going to end up with a carbon-nitrogen double bond, still bonded to the R group, and let's draw this on the same side, keep some consistency. Positive charge, and again, this would be resonance stabilized. Part of that positive charge is shared on that carbon, but oftentimes, again, you won't see it drawn. And then you'll also have formed some water. And then we just need to deprotonate this to get to our final product with that carbon-nitrogen double bond. And again, anytime you need a base, use your amine as the base. And when he deprotonates, you also get some of that conjugate acid back. So, and there we're done. We've now formed our imine. Now, I'm not going to take the time to cover it. So, however, if you had to show the mechanism for hydrolysis, it would be the exact reverse order of steps. First thing you'd want to do is get from here to here is you'd protonate the imine. And what would you protonate it with? You'd protonate it with the conjugate acid of the amine. So you'd protonate it. So then you'd come back and you'd have water do nucleophilic attack. So this water would come and attach right here, kick the electrons up, leading here. And you just work your way back, exactly the reverse of the mechanism. All right, so now that we've seen the mechanism of this, we want to look at, okay, well, how do we predict the products of hydrolysis? So it can be a little point of emphasis in some classes more than others, and it can be a little bit tricky, especially when you start dealing with cyclic imines. And we spend so much time focusing on the forward reaction, forming the imine. Since this is a chapter on ketones and aldehydes, very little is spent on the reverse reaction, but we want to spend just a little bit of time there now. All right, so this is the lovely imine reactant. We can tell it's an imine by that carbon-nitrogen double bond right there. So here's our imine reactant we're going to do hydrolysis of, and we're going to find out that we're going to end up breaking this carbon-nitrogen double bond, going back to a carbon-oxygen double bond. And just like with acetals, I highly recommend if you're trying to predict the products, easiest way to start is just to redraw your reactant nice and big. All right, so there we've redrawn the reactant nice and big, and we're going to go back and erase that double bond to nitrogen. So we'll start there, and this carbon, instead of having a double bond to nitrogen, it's going to have a double bond to oxygen, and this nitrogen is going to gain his hydrogens back. So we're just adding the H2O, the water, back in this hydrolysis reaction. And so I've drawn it like this, and there's nothing wrong with drawing it like this, but you might also, if you're taking a multiple choice test here, maybe it might be more likely drawn like so. And one thing to note, we've done this under acidic conditions, and amines are bases. And so if this was multiple choice, it wouldn't be surprising if this actually ended up protonated as an NH3+. So it really just depends on how acidic your conditions are and stuff like that. But in all likelihood, it probably would end up as an NH3+. So, but you technically could see it either way, as an NH2 or an NH3+. Either one is a likely multiple choice answer, but NH3+ is probably the more technically correct answer here in this case. But that's how you predict the products of the hydrolysis of imines. So now we'll deal with enamine formation, and enamines occur when you add a secondary amine here, and this is a very common cyclical secondary amine that's used in enamine formation, but it definitely doesn't have to be cyclic here. But again, using two different size rings makes it easy to keep track of where things came from in the final product. And it turns out in this case, instead of a carbon-nitrogen double bond, in fact, let me just start there. We'll start with a carbon-nitrogen double bond. So it turns out this is an intermediate along the way. Problem is that in this case, we're still going to form some water. And we know where the O comes from, and we know where one of the H's comes from, but where does the other H come from? With the primary amine, the nitrogen had two H's to lose. Well, this guy doesn't. And so it turns out that one of these carbons actually loses a hydrogen in the process. So we can kind of see like losing a hydrogen, and we'll come and deprotonate. These electrons dump in here, and these electrons push back up to the nitrogen. So that way your final product, instead of having a carbon-nitrogen double bond, has a carbon-carbon double bond. And looks like so. And it's this guy that we call the enamine. And you can see why they call it so. So the ene part is the alkene, and the same carbon's also involved in having it being part of an amine as well, hence the name enamine. Cool. And so that's your enamine resulting from the addition of a secondary amine. And now we've got to talk about the rest of that mechanism as well. And we're going to find out it's very, very similar to imine formation, except the way it ends. So, and the way it ends is where we form the ene part. And again, it's just the fact that our nitrogen only has one hydrogen to lose, not two. So we had to lose the second hydrogen to form the water somewhere else. Let's take a look at that mechanism. All right, so just like with imine formation, I'm going to show how to predict the product with a very specific example, but now we're going to work the mechanism with a very generic example. And just like with imine formation as well, the first step, amines are better nucleophiles than alcohols, and once again, it's nucleophilic attack. Push the pi electrons up, we'll form an alkoxide. We'll end up with this situation again where we've got a negative oxygen alkoxide and a quaternary amine ion with a positive charge. But again, the negative oxygen is a strong base. That alkoxide is a strong base. The quaternary amine is only a weak acid, so we'll have the strong base react first. And just like we saw with imine formation, when you need an acid, your amine is going to be protonated by the acid in your solution, and that's what you're going to use. And so anytime we need an acid in this reaction, it is this protonated secondary amine that we'll use. Cool, and when we deprotonate that guy as well, we end up with some of our secondary amine. We end up with this lovely species, and just like we saw with imine formation yet again, now we'll deprotonate the nitrogen to produce a neutral intermediate species. Cool, also formed some of the conjugate acid back yet again. And once we have that neutral species, again, there's nothing particularly reactive. We just have to keep in mind where we're headed. And in this case, we are headed to having this hydroxyl group gone, but it's not a good leaving group. How do I make it a good leaving group? Protonate it. Common pattern we're seeing with the acid catalysis here. Once you form a good leaving group, you always have it leave in the very next step. And yet again, we're not going to, looks like we're forming a carbocation, but this one will be resonance stabilized. And once again, we often draw only the more stable of the resonance structures with the positive nitrogen instead of a carbocation. And that takes us right here, and just like what we saw back here, once you've got that carbon-nitrogen double bond, and oh, up here I forgot to give it a positive formal charge. Once you're there, you're going to end up deprotonating one of the adjacent carbons to what used to be the carbonyl carbon. So we've got to draw one of those hydrogens in, like we'll do right here. And then once again, once we need a base, we always just draw in some of the amine to do it. So in this case, we'll draw in another equivalent of our secondary amine. He's going to come and deprotonate. That frees up these electrons to form the pi bond, pushing these back to the nitrogen, forming our final product here. We've got an alkene there. And there's our enamine. Cool, also forms some of the protonated amine, just to be thorough here. Cool. Once again, if you add H3O+, it just reverses all the steps all the way back, and you might be on the hook for that mechanism as well. And once again, I'm not going to cover it specifically, but it is one you should practice. And you notice the first thing that happens to get there is you need to protonate this carbon and put a hydrogen on there. Where do you get that from? Well, you get it from the corresponding acid right here. You'd just go down, you'd push these electrons down and come and get that proton to get here. What would you do from there? Well, then you'd have water come, and instead of leaving here, you'd have it come and attaching, doing nucleophilic attack and attaching, and you just do the exact reverse all the way through. 6 steps in both directions. My apologies. All right. And with these hydrolysis reactions, much more likely is you're going to have to be able to predict products. And once again, I'm going to give a little tricky one so we can get a good schematic for how to predict those hydrolysis products. So I picked another cyclic tricky one here, but first thing you'd have to recognize that this is an enamine, because this carbon right here is part of both being an alkene, enene, and an amine, enamine. And so with hydrolysis here, we're going to break this carbon-nitrogen bond. So, and this one's not so straightforward, but same thing. I'm going to draw the reactant over again and then modify it accordingly. All right, so first thing I'm going to do here is I'm going to go erase that carbon-nitrogen bond that we're going to cleave. So So he's gone. And then also this alkene was not a part of our original reactant had we been forming the enamine. So, and where we had a carbon-nitrogen bond, instead we had a carbon-oxygen double bond. So, and in this case, we're going to add the hydrogen right back here as well. In fact, let's do this and keep our color straight. We'll add a carbon-oxygen bond right there, a hydrogen right there, and we're supposed to add the water back. Well, here we added an aldehyde. That's great. And oftentimes we draw this hydrogen in now, but that's not the hydrogen we've added. That hydrogen has been there the whole time. The other hydrogen actually got added right here. So notice in here, we've got 4 bonds. 1, 2, 3, 4. There's no hydrogens on that carbon. There is now. And so we've added the water back, 2 H's and an O, to predict what this looks like. And once again, this might be drawn a little bit different here. If you're given a multiple choice, it could be drawn like so, or you might see maybe something a little bit like that. Not too different in this case. But that is your product of hydrolysis for your enamine, and something you may very well be likely on the hook for. All right, so now we're going to revisit the Wolff-Kishner reduction here. And before we can talk about the mechanism of this reaction, we really need to learn about imine formation, or technically hydrazone formation. So it turns out, again, we learned just a second ago that when you start off with hydrazine and a ketone or aldehyde, it forms a hydrazone, and that's actually the first part of the mechanism. And the mechanism is exactly analogous to what we saw with imine formation, so that's not the part of the mechanism that's going to be new, but I do want to focus on the parts that are new. So, but reminder, with the reaction of organic aromatic compounds, we often did Friedel-Crafts acylation and formed a benzyl ketone here. So now we'll return and look back at the mechanism for the Wolff-Kishner reduction. And it's just a reminder, the Wolff-Kishner reduction reduces a ketone or aldehyde all the way to an alkyl group, so complete deoxygenation. Back in the aromatic compounds chapter, we often did Friedel-Crafts acylation followed by reduction. And in some cases, we could make different alkyl benzenes that maybe we couldn't make with a Friedel-Crafts alkylation due to like rearrangements and stuff. So in this case, it turns out the first step deals with the hydrazine, and it's going to form that hydrazone. And again, this part of the mechanism is not different from what we saw with imine formation, so I'm not going to cover it again. So, but this part of the mechanism alone is 6 steps long, which kind of sucks, but we do form a hydrazone, but it's what happens from here that is going to be new. So when the hydrazine reacts, we get our hydrazone, but then what's the KOH and the heat do? Well, KOH is a strong base, and we're going to need to lose all of this and replace it with a couple hydrogens. And how does that happen? Well, in this case, your KOH, there's your hydroxide. It's just going to come and deprotonate this nitrogen here. It's going to form this lovely species, but this lovely species is resonance stabilized. We can draw the other resonance structure here. And we can see that the negative charge is not only on the nitrogen, it's shared on this carbon right here as well. And so we've deprotonated it from the nitrogen out here, and now we're just going to protonate that carbon. So when the hydroxide takes that H, it forms water. And that's what we're going to use to protonate here. And so in this case, we're just going to come grab one of these protons. And now we've added an H there. And I don't technically need to draw that H, so it's bonded to a carbon, but I'll draw it in just for clarity's sake here. So we've also formed some more hydroxide. All right, and then we're just going to repeat that process over again. We'll have hydroxide come and deprotonate the other hydrogen right there on the nitrogen as well. All right, and then from here, we're just going to pour these electrons into here, push these to here. And if you look at what we've done, we've actually formed a nitrogen-nitrogen triple bond. That's nitrogen gas, and it bubbles out of the solution. And then we formed a carbanion on top of that. And that carbanion just needs to get protonated by water, just like we've done here. Cool, and we formed a little more, regenerated some hydroxide there. But there's our final product, so complete deoxygenation of our ketone. That's the mechanism for that Wolff-Kishner reduction. And again, we really needed to cover imine formation, which is analogous to hydrazone formation here, before we could cover the rest of the mechanism for this. So you are much more likely to be quizzed on the last part of this mechanism than on the rest of it. And some of you would actually have seen this mechanism back in the aromatic compounds chapter. So, but a lot of books find it more appropriate to discuss it here. Now, if you found this lesson helpful, would you consider giving me a like and a share? Best thing you can do to make sure that other students get to see this lesson as well. If you're looking for the study guide that goes with this lesson, if you are looking for practice problems on ketones and aldehydes, check out my premium course at chadsprep.com.